your notes, and also we did that in the previous class. I just needed to emphasize a point here that's very critical. If you look at the construction of this ladder diagram, you can see clearly that we identified three main field devices, the devices that are connected to the PLC. And we see clearly, and it's labeled, that the start button is a normally open button. You can see it's an open switch. The stop push button is normally closed. You can actually see that it is closed. It's completing the circuit already. And of course, the overload, which is inbuilt into the system, is also a normally closed switch. You can see even from the symbol, it's already a normally closed switch. Now, if you look at the symbols used in the ladder diagram, this is where I wanted to emphasize. Look at the symbols used in the ladder diagram. We've already identified a normally open contact for the start push button. We have identified the stop push button and the overload as the normally closed contact. So these ones are given normally closed contact. Now, when we say this is the rule of thumb, we do not mean that the symbol used for a normally open contact is used for the start push button. I'll say that again. We don't mean that the symbol that we used here, because you can see that the normally, because this is I0.0, the normally open contact is used to represent the start push button. That should be visible here. But notice we are also using a normally open contact. We are using a normally open contact. Look at that, to represent the stop push button as the symbol. We are also using a normally open contact for the overload relay. And this is purely based on logic. And we know, and that is what I wanted to explain, the logic of using, because somebody would ask, why not use a normally closed contact? Because it's a stop push button. Why not use a normally closed contact? Because it's an overload relay. And that's the logic I want us to look at. So let's look at it this way. Let's use logic, because this is purely based on logic. That's why we are calling them logic diagrams. For the normally open contact, for the start push button, the start push button, if you can see clearly, is already open because it's open. Okay? And therefore, if a switch is electrically open, in logic, it's represented as a logic 0. So that when you close it, now it becomes a logic 1. So the normally open contact that is used here is in order, because the start push button is always in the open position. So electrically, it is open. When you convert that to a PLC or a PLC logic, then now it's logic 0. So that when you close it, then you get a logic 1 going into your symbol, your normally open contact. Now, let's use the same logic for the normally closed contact. So assume, for example, we know exactly the reason why we use normally closed contacts. It's like an emergency stop or even a stop. You want to press a button, and as soon as that button is pressed, you expect the machine that's upstream to stop working. That's why it's a stop push button. You want to stop the operation of the equipment that you're controlling. So you expect that when you press a button, the machine is going to stop. Now let us look at it logically. If this was a normally closed contact, let's just have one normally closed contact. So we have a switch somewhere. You've got a switch. Okay. So that's your switch, which is normally closed. So that's a normally closed contact. And then upstream, it is connected to a normally closed contact. Because we were saying, what if we decide to make this a normally closed contact and that a normally closed contact? So now, remember, this is already at logic 1 because it's closed. So when it is at logic 1, it's a closed switch. If we were to use a normally closed contact is like a NOT gate. So if this is logic 1, when it goes through the normally closed contact, it becomes a logic 0, meaning logic 0 is transferred to the output. Now, if it is pressed, if I press the normally closed, if I press this button here, I'm opening the circuit. So electrically, the circuit would be open, and so a logic 0 is transferred into your logic. So if you press this button, we open the circuit, and because this is a NOT gate, we get a logic 1. Now, see the problem with that. When you transfer logic 1 to the output, you expect the machine to operate, because the output module will actuate the motor starter and the motor would start running. But the reason for pressing a push button, this closed stop push button, is because we want the machine to stop. So you can see the contradiction that if by any mistake, let me do that again so that it's home. By any reason, if this, because it's already closed, if it is pressed, if you press a stop push button, when you have this as a normally closed contact, you are going to open the circuit. And so a logic 0 is going to be transferred to the NOT gate. We know what happens when a logic 0 is transferred to the NOT gate. Because a NOT gate, or no, let me just call it a normally closed contact, when it's having a logic 0, then it's allowing logic to pass through. When you give it a logic 1 or a logic high, then it now blocks logic. So here, it's given a logic 0. By virtue of opening this, you've opened the circuit here. So if you've opened the switch, then you give the normally closed contact a logic 0, and it converts that to a logic 1. And so that logic 1 is transferred to the output. So we cannot use a normally closed contact here because it's like we'll be negating the effect of the stop push button. So then if somebody presses the stop push button, the motor will be running, which is wrong. When somebody presses the stop push button, the motor should stop working. That's the same thing with the overload relay. The overload relay switch is such that if there's an overload of current that is sensed by this switch, then it's supposed to stop the motor immediately. But if you connect it to a normally closed contact, the moment it senses an overcurrent, it's supposed to, because it's already normally closed. You can see it's normally closed. So if it senses an overcurrent, it will open. And if it opens, it will send a logic 0 to the symbol here, to the normally closed contact. And so if it's a normally closed contact, it will provide a logic 1. So if it gives a logic 1, the motor will continue running. And an overload should stop the motor from running. Okay? So therefore, and this is now why I was bringing this, I wanted you to understand that for us to have a proper operation of our PLC, the stop push button at the point of the field device, it is in the closed position. But in the symbol, we use a normally open contact, so that the combination of that normally open contact with the closed position of the field device will affect the motor appropriately. Because in this case, you can actually see that at this point, because it is already closed, it is at logic 1. That is that electrical signal, if converted to logic, it's logic 1. And that is why you see the normally open contact is already highlighted, meaning it is already active. It's passing a logic 1. The overload switch is already a closed contact. So we already know that there's a logic 1 there. And that is why you see that logic 1 has been transferred to the symbol there, so that it is also highlighted, so that it's also passing logic at this state. So that is very important for us, so that when it is pressed, you get a logic 0. And when you get a logic 0, you press the button, you get a logic 0. And when you get a logic 0, then you'll make the subsequent normally open contact. And when that becomes a logic 0, then the output definitely becomes a 0. Because remember the combination, these things are connected like this in series. So that any one of them, if any one of them goes to 0, then the output goes to 0. Okay, so it is important to always remember, as I leave this note now, that the normally closed contact is used at the field device point, but connected to a normally open contact on the symbol, the PLC symbol part. That is when the operation can work. And you can go and try it at home. Make this a normally closed contact and see if it will work. You'll see that the logic will not work. So a normally closed contact is used in conjunction with a normally open contact symbol. Hope that is clear. Good. So now allow me to move on to what I need to talk about today. I think it's, okay. I need to get out of this and move to my subject of discussion today. Okay. So today I want us to continue our discussion on ladder logic programming. Ladder logic programming. And I will try and emphasize what I've just said again here. So the reason why I want to talk about this is specifically because I want to talk about the latching, because we'll use that in the subsequent examples that we are going to look at. So usually we create a ladder diagram. That ladder diagram is to accomplish a specific task. But just like in code, the text code that we usually do, C++, Java, and C# and whatever, you can write a piece of code that is reused several times within your program or even in another program. So there are certain pieces of code that can do a certain or perform a certain task. They can be repeated within the same program that you have written, or you can even call it and use it in a different program. In the world of text-based programming languages, we call them functions. So you have built a function, and you can always call that function at any point or even several times within the program that you have written. Alternatively, you can even call that function in another different program that you're writing. But that function is just a group of code that performs a very specific task. So you can always call that code every time you need to perform that task. So that also happens with ladder diagrams or logic programming, that there are certain programs or that we can write and then use them. We can use them severally within the program as needed. The only challenge, therefore, is to make sure that we draw our ladder diagram in such a way that it does not slow down the overall programming time. You want to make sure that your programming ladder diagram is still as optimal in terms of speed. Otherwise, it will slow down, because remember, these things are all about storing information in different memory locations or memory addresses. So if you write a program that is windy and keeps repeating itself, chances are that the overall programming time will be longer. So the program might take long to execute. And that might not be needed in certain cases, especially where you want to do repeated processes and very fast. Okay, so constructing a program becomes a simple matter of just getting the appropriate ladder logic that you had written and then connecting it to your main ladder diagram that you want to connect. So we can look at some few examples. One of the functions, and I say functions in quotes because I told you in text-based programming languages, we call them functions. You can build a function for calculating the area of a circle, so that within your program, every time you need the area of a circle, you call that function. And by calling, because you don't have to write the program again, the fact that you've called the function, it's going to, the processor will automatically perform the operation of that function, meaning it will calculate the area of a circle and provide a solution there, so that you minimize the lines of code that you use. Because you can imagine if in your program every 10 steps you want to calculate the area of a circle. You can't be putting a ladder, you can't be writing a program every 10 steps. You write a ladder, a program that calculates the area of a circle. So you can write the program that calculates the area of a circle once, and then each time you want to calculate the area of a circle, you call that program, just like you do with functions. So in ladder diagram, one of the most important functions, quote unquote, that we use is latching. So that's what I want to discuss today. So what is latching? Latching is one of the most important pieces of ladder diagram, ladder logic programming. Very, very important. So latching simply refers to the change of state, or to, let me just say to, latching refers to changing the state of an output to true, or to logic 1, or to logic high, holding that state. There are 3 steps: holding that state, until, holding that state, let me use the correct word, holding that output state as true, until certain conditions are met. Until certain conditions. So once those conditions occur, then the latching circuit will have to return, returning the state of the output, or the output state, back to false. This is very critical. That's why I tell you it's like a 3-step thing. Latching is just to ensure 3 things. You use a latching circuit in PLC. The first thing that latching circuit does is to change the output state to be true, or to be logic high. Then it holds that, or it holds on. It holds on to that state. That's why we use the word latching, because latching in English is like, if you latch on, is something. And so first, change output state true, hold on to that state, that true state, until certain conditions occur. Once those conditions occur, then you turn the output state back to false. So it is what, in other words, we can usually call then a reset is done, meaning it returns the output back to where it was originally. Okay, so there are only 2 methods. So latching in PLC, latching is achieved through 2 methods. Number 1, what I've just called the set and reset instructions. So this is one way of achieving the latching. Okay, or other books will just call it latch and unlatch. Okay, they'll call it latch and unlatch. The other method that can be used to achieve this latching, where the output is set, is changed to a state of true, then you hold on to that state until a certain condition occurs, and then you return the state back to false. That is known as, or the other method is known as latching logic. Other books will call it a hold in logic. A hold in logic. So these are the two main methods of achieving latching. We want to look at both of them quickly and see which one is most preferable and why. And then we'll use it in subsequent examples. In fact, latching will come a lot of the times that we are drawing our ladder diagrams, proper ladder diagrams, not the two rungs or 3 rungs ladder diagram. Rungs that are 5, 6, 7, 8. You'll see that latching can be used several times to help with certain instructions. So let's start with the set and reset, because I probably need to explain that. Okay, so we'll start with the first method, which is known as the set and reset. Set and reset. Okay. Now, I've told you that certain PLC manufacturers don't want to use the word set and reset. In fact, I remember even Alan Bradley, the Rockwell automation that we, the class book that we have, uses the word latch and unlatch, but it means the same thing. Other, like Siemens will use set and reset. Okay, but it means the same thing. I just told you these are just preferences by manufacturers to sound different, but they're talking about the same thing. Okay, now in the set and reset instructions, these are just simple functions. Okay, and the beauty of the set and reset instruction is that the symbols that you use for the set and reset instructions don't have to be on the same rung. They can belong to different rung. The only challenge is whenever you have symbols. So what I mean is you can have the symbol for set and reset. So set can be in one rung. So of course, let me just pretend that I've drawn another diagram. I'm going to draw another one, don't worry. So, or maybe even this one is also connected to, okay, like that. So you can see that set is on rung 1 and reset is on rung 2. Remember, the set and reset or the latch instructions are output instructions. So again, now I've introduced one. We are used to the normal coil as the output. So this is actually output Y. Okay, the set and reset, these are output instructions. So they are a form of the output. Just like you have one input is a normally open contact, another input is a normally closed contact. So here you have just the normal output, but you can have a set output, you can have a reset output. I think we did these symbols and we have those symbols in the notes already. So the set and reset are just output instructions. So you have to be very careful how you represent them. Notice they're also on the right side of the ladder diagram. So what I was trying to say is for the set and reset, you can see that they don't have to be on the same. They're actually not on the same rung. Each one of them is on a different rung. Now, the problem with having these on different rungs is it means therefore ultimately you'll have more rungs. So whenever you're doing debugging, when you're trying to check where a problem is, it can be very difficult because the set and reset symbols can appear severally in different parts of the program. So they can be in different ranks. So set can be in rank 1, reset can even be in rank 15. They don't have to follow each other sequentially. So here is just for illustration to show that they're in different ranks. But sometimes you might have a program where there are other programs in between so that the reset only appears much later. So it means therefore that whenever you're debugging your code or you're debugging your program, you might have challenges debugging because the set and reset are in different ranks, okay? However, now we can do it properly. So typically, and this is just to illustrate them, to show how we construct the set and reset, or the latch and unlatch program. I drew an example there, but it was not very clear. So here I have to do it again so that we are very clear. Remember, this is just to illustrate that they're in different ranks. The ranks don't have to follow each other. They don't have to follow each other. So this is the set and this is the reset. So this could be an input A, this is an input B, so this is your output Y. Let me just say this is input A, this is input B, right? So this is also output Y. Okay, so notice that they are both outputs Y. They are both output Y, meaning, and this is very, very important. The memory location for your output, because you have your output Y, the memory location of your output is the same memory location of the set, and that is also the same memory location of the reset. So that whenever you activate the set output, it affects whatever is located in that memory location. And whenever the reset instruction is also carried out, it affects whatever is in that memory location. So the output is one. This is one thing that you have to remember. The set and reset are instructions of the output. So the output is one. So it has the same memory location or the same address. That's why this is output Y, and this, the second one is still output Y. The set is output Y, the reset is output Y. But whenever you do the set instructions, it will affect what logic is stored in the output. Whenever you do you carry out the reset instruction, it also affects just what is in that same memory location or that output Y. So this is just talking about the same output. So let's see how this works. Let's see how this works. So sometimes you can have both inputs as false. So usually, if you want to see how this works, the best way is always to try and use, you have two inputs and you have Y. So you've got to see how these things work, like what would be the output for each of the cases that exist. So the first instance is when both A and B are false, 0, 0. That's the first case. What happens to the output? So clearly, when you have A and B as false, then it means this is logic 0, this is logic 0. So the output does not change. It retains the state that it was in, because nothing changes the output. Remember, the input will only change the output when it receives a logic 1. Okay? So in this case, I can just indicate that when both A and B are false, then the output does not change. The output Y does not change. Because you cannot assume that every output is a logic 0. Sometimes the output is already a logic 1 before it receives instructions from the input. So whatever was at the output does not change. It remains there, okay? That is when both A and B are 0. So if the output Y is false, then it stays at false. If the output Y is true, then it stays at as true, okay? How about you now change what happens? Okay, let's change what happens. So let's say if input A goes to true, if input A goes to true, that is now 1, 0. Okay, the moment input A goes to true, let me just say momentarily, because as soon as input A goes to true, remember what usually happens. You go back here and check. If you make this a logic 1, definitely it will activate the set instruction. So the set symbol changes the state of the output. So if input A goes to true momentarily, then the set symbol changes the state of the output, changes the state of the output, Y to true. Because remember, whenever you have this like that, so if you make this logic 1, then this becomes logic 1. Okay? It follows the state of the input. So in this case, again, momentarily, remember, we've just made the input A as logic 1. So the set symbol changes the state of the output Y to true. But remember that scanning happens by, see, scanning will be, it will start from here, run like that, then come back and start from here again and run like that. Then that's one scan cycle. And then it repeats, goes back again to the top left. Okay. But so after a subsequent scan, if the input A changes to false, so you notice the first thing that changed here was having a logic 1, and that made the scan, the set symbol change the output to 1. And then the rest didn't change. Remember, we just said it is only input A that changed its state to 1. So then everything else remained the same. So the output is set to 1. The output is set to true, in other words. Okay. So after a subsequent scan, if that input A now changes back to false, it does not affect the output because we have said that the set is a latching circuit. So what happens is, first set the output to state 1, hold on to that state until some condition is met or a certain condition occurs before the output changes back to false. So I can actually indicate here that if so, after subsequent scans, if input A changes state to false, changes state to false, the output Y is not affected. Okay? In other words, we say that output Y is latched true. Okay, I'll repeat that. Remember, initially, input A and B are both 0. Clearly, it means that the output will retain its position, its state. In this case, 0, because input A and B was 0. So the output Y retains its state. Okay? You've just changed input A to logic 1 or logic high. What happens, therefore, is that the set aspect of our circuit here, or of our diagram here, will change the output state to 1. Just like if you set your watch, we used to have these watches that you set. So when you press the set, it sets it to a certain position. So the output in this case becomes state 1 or state true because it's been set there. However, because this is a ladder diagram, the scan cycle repeats itself. So even when in the repetition of the scan cycle, if the output changes back to 0, I mean, the input A changes back to 0, that will not affect the output Y because the output Y will latch onto the state that it was set to until a condition is met or until a certain instruction occurs. So even if the inputs now change their state, its state back to 0, that will not affect the output. The output will retain its set state until a certain condition is met. So that's why we are saying the output is latched true. Okay, so it's very interesting. It's very interesting to note. In fact, let me draw. If you were to put this in a software, then that condition would be like this. I'm going to use, remember, I'm going to use a different color to denote which lines are active. Okay, so it would be like, so that means the rail here is activated. So you'll have the input A was logic 1. So let me call this input A. That's logic 1. And we said that as soon as the input A is set at logic 1, notice it's green, meaning it's now been activated. So that's logic 1. Then the set symbol also activates the output. So you have your output Y here. But now notice the output is logic 1. Why is it logic 1? Because we have activated A, input A. It's at logic 1. So the only guy that is still at logic 0 is input B. Okay? Input B is still at logic 0. Okay? Now, please note, I said that the output is the same. The output is the same. So therefore, this is still output Y. Let me indicate that again. So you can see it is still active. So this is basically meaning this is logic 1. Let me use, this is logic 1 or high. This is now logic 1. And of course, logic 1. Why? Because I told you set and reset are instructions of the output. So they are in the same memory location. So the moment the set changed the state of the output to logic 1, even the reset aspect is just, because it's still the same memory location, it's just one. Nothing, they cannot have different states. You cannot have, that's what I mean. You can never have this one. You can never have these two to be of different states. So you can never have something like this. Okay? Why? Because the set and reset are in the same output location Y or output address Y. So if the set is a logic true, the reset is also logic true because they are part of the, in fact, they are outputs. Okay? So I hope that is very clear. So let me return it to how it was. Please mute unless you're asking a question. So we have this reset like that. Okay. So this is when what happened, we've just said that during the first, when the input goes true, then of course the set symbol changes the output to logic 1. Okay. Now, this step here, this step that I've just mentioned, this step where you have subsequent scans, it means we are now changing. So let me try and do that. When now A goes back to 0. So let me draw it in a different color. So if A goes back to 0, if A goes back to 0, we have just indicated here, if A changes state to false, the output Y is not affected because it is still latched. Okay, so the output Y will not change. Okay, so basically it's even the same diagram can still represent it, because even if I change this back to 0, that's what I mean. Even if this goes back to 0, okay, later, not during the first scan, later, if you change this back to 0, then the output stays at logic 1. That's what we mean. Now let's go to the other condition. Okay, let me leave it like this for a while so that we compare it with the next diagram. So now what happens when input B changes to true state now? Because we've seen where both were 0, 0, then A went to 0. How about now if we have input B changing to let's see 0, 1. So let's input B changes to state high. So when input B is activated now, changes its state to true, let's see what happens. The output Y will change state back to false. In fact, the best way to put it, let me use proper, allow me to just use, because I need you to understand. Let me just say, when input B changes its state to true, then the reset symbol, then the reset symbol changes the state of the output, changes the state of the output Y back to false. So we say that the output, therefore, the output Y is unlatched. The output Y is unlatched. So the only way that the output changes back its state is if input B changes its state to true. So what happens therefore is we can draw this diagram, remember. So now we input B changes its state so that A went back to 0, okay? It is only B that has gone to logic 1. So this is A, this was B, and this is A, okay? And now what happens is when that happens, this guy goes back to 0. Okay, so this is output Y. So B is the one that has gone to logic high or logic true. So it means that it is the state of B that resets the output Y. Okay, so remember the latching instruction was first you take the output state to logic high or logic true, hold on to that state until a condition is met before that output state changes back to false. So in this case, this guy sets the output to logic 1. First condition is met. The output is held on to, even if this guy goes back to 0, the output is held on to up until this guy goes to logic 1. As soon as this guy goes to logic 1, it resets the output back to false. That's why we are calling it a set reset instruction, set reset instruction. So it is only when the input B, that is the condition that must occur, when the input B changes its state to true, that is when the reset symbol will now return the output state back to false. So we say that the output has been unlatched. All this time, remember, every time the PLC scans from left to right, top to bottom. So it goes like that. That's one scan cycle. Then it repeats, okay? So the PLC will run from left to right, top to bottom. So in case where both inputs, so remember we didn't do the 1-1, but if both inputs, I can even indicate that, if both inputs A and B are true at the same time, it's a state for 1-1, at the same time, then The ladder diagram evaluates the first rung. And output Y is set to true. Then the second rung is evaluated and output Y is set to false. At the end of the scan cycle, the state of output Y is updated as false. I hope this makes sense. Let me explain it in myself before we carry on, because we now need to move to the second part. So we are saying this: in a state where both A and B are true, a condition where both A and B are true, will be having this. This is A, this is B. Both of them are true. Let's see what happens. So that's for the output Y. So because the scan cycle moves from left to right, top to bottom, okay, the first thing that will happen is the processor for the scan cycle will first go to the logic of A and find that it is 1. Remember, we had said as soon as A is set to logic 1, then the set symbol will convert the output to true, okay? So the output would be 1 or true. Is that okay? But because the scan cycle still will be running, it will come and find that B is also 1. And whenever B is 1, that was the instruction to reset the state of the output. So it will then find that B is 1, and what does it do? It resets this to false. And the state will just know, and when the scan cycle is complete, that is when it updates the status. So every time I write true here, it's like it's stored in a temporary location. It's like it takes note of that state. But when the scan cycle is complete, then now each state is updated. I think we spoke about this when we were talking about scan cycle, that during scan cycles, the instructions at the inputs are read out because those are logic expressions. But the state of the output is not updated until the scan cycle is complete. So it's like, just take note that we've left this state to be logic 1. Just take note that this state is now logic 0. But when now we complete the scan cycle and realize that we have completed the scan cycle, then now you can update the state of the output as appropriate. So please note that that's what I have indicated here, that because of the scan cycle, we'll start with the state of A, okay? And A is for set. So the output would be converted to a true state. And then quickly, because the scan cycle continues, then it finds that state of B is also 1. So what does it do? Because B is the condition that resets the output. So because the B is logic 1, input B is logic 1, then the reset symbol changes the output state to false. Then at the end of the scan cycle, those outputs are updated accordingly as true and false. So ultimately the output will be false because that is where the instruction ends, or the scan cycle ends at. But that is only in the case where you have both of them as 1, 1. You've seen the condition where A is 1, but B is 0. If A is 1 and B is 0, then what happens? We just have the set. So the output would be logic true. So that even when you return A to 0, the output is still logic true. The only way this output will change its state is by making B logic 1. Then the output will go back to false. That is the set and reset instruction. Please, I will see if I can put proper notes down that you will understand when you read. Because of time, allow me to do the second part, because that's important. In fact, it is the one that we'll frequently use. So I think it's important for me to actually do it before the end of the class. So the second way of achieving the latch was through, we indicated it, the second way of achieving the latch instruction is through, we called it a logic latch. Or let me just say with hold in, okay? With hold in latch. We are holding in. So we are using a hold in logic to achieve latching. Now, the outcome is still the same. This is still a set and reset. So we still use even the same, we still use the same logic as we have done previously. The difference here is, and please take note, when we use the set and reset, we used the symbols for set and reset. Okay? But when we use the hold in latch or the hold in logic, in fact, I should say with hold in logic, not hold in latch, with the hold in logic. So we had logic latch with hold in logic. When we use the hold in logic, we achieve the same outcome as the set and reset instructions. But this time round, we are using, we are combining our inputs and outputs in a certain order to achieve the set and reset logic. Please note here, we are not using set and reset. So you will not see me use this set and reset symbols. These are only for the set and reset instructions. The first case. The second case does not use these symbols. It uses a combination of inputs and outputs, but to achieve the same outcome as the set and reset. So, to achieve, let me just say to achieve latching, using hold in logic, what do? We don't use the set and reset symbols, but we let me just say both inputs A and B are connected on the same rung as output Y. Now, please note that this case for set and reset, the first thing we said was that they are in different rungs. Set and reset are in different rungs. Here, first of all, we don't use the set and reset symbols. Number two, A and B are not on the same rung. They must be, are not on different rungs. They must be on the same rung. Okay, those are the differences. The outcome is the same. Okay, the outcome is the same. Now, something to note also here in this case, before I even draw the circuit, is something to note here is that input B is a normally closed contact. And output Y is used twice. Okay? And branched, or what we say, it's connected in parallel. In parallel with input A. Okay? So let me draw the circuit for it to make sense. Here, we don't have the set reset because this is a different logic, but same outcome. So here, what we do is you connect A. So you have input A connected there. You connect it with input B. So notice here, they are on the same rung. Input B. But we have said that input B has to be a normally closed contact. Okay? Then they are connected to the output Y. So we are not using the symbols, output Y, connected to the output Y. But again, notice from the note that I've put here is that the output Y is used twice. How do we use it twice? We branch it with the input A. You branch it with the input A like that. So this is output Y. Okay? So this is how to achieve hold-in logic without using the set reset symbols. This is how to achieve the hold-in logic. Input B has to be a normally closed contact. Okay? Now, if I were to draw this, using a different color to denote the state of each case, we know very well, so if we provided, if we energized the rails.
Excuse, sir.
Oh, yes, go ahead.
There is an hand raised by Alphonse.
Sorry?
There is a student raising his hand. Maybe he got a concern.
Oh, okay. Thank you for notifying me. I think I need to check that because I can't access it from the device I'm using. So I have to use a secondary device to check your comments. I see. Okay. Oh, there's a student raising their hand. I can't see the hand up.
Yeah, Alphonse.
Okay, please go ahead. Go ahead. Sasa waongei.
Maybe it was a mistake, but he raised for a while.
Okay. Now, please note. Thank you for notifying me. But please note that whenever I am presenting, I am not able to see when you raise your hand. So just interrupt me like you've done, and I'll take note of that, and you'll talk. But if you just raise your hands, I will not see. You can put in the comments. I can check them later towards the end of the class, and then respond before we end the class. But if you want to interrupt immediately, just speak. No problem. Anyway, so please note that we are using a different hold-in logic, and in the hold-in logic, we've said that the conditions are we must have input B as a normally closed contact, and we have to branch the output Y with input A. So the outcome that is achieved by this circuit is exactly the same as the outcome that is achieved by our original circuit for the set and reset. It's only that the set and reset were using their own unique symbols and they were connected in different rungs. Okay, but for the hold-in logic, our inputs are on the same rung as the output. and the output is branched out to input A. So for us to understand the logic, let's see how it works. I was just about to draw, for us to understand the logic, I was about to draw a case where if you activate the rails, what happens? We know that the original state is such that the input A is logic 0, of course, that we understand. But the input B is a normally closed contact, meaning at 0, it is already allowing logic to pass through. So allow me to draw it like that, because it's already allowing logic to pass through. Please note, again, let me just take a breather here. Remember, we had said we have two conditions for the normally open contact. So for the normally open contact, let me say this is false and this is true. This is logic 0, this is logic 1, or high, or whatever. If this is false, then we have it like that, meaning it will show as inactive. In your software, it will be black in color. But if it is true, the normally open contact, if true, then it will change color to green, meaning this one is passing logic 1. It's allowing logic 1 to go to the output. The first one is blocking the logic from going to the output. The opposite happens with the normally closed contact. When the normally closed contact is false, it is allowing logic. So you will actually see it on your screen as green. It's normally closed, but it is green. The moment it's green, you know it is allowing logic to pass through. So the logic would go to the output. And for the normally closed contact, it allows logic when its state is false or 0. But the moment you activate it, you give it a logic 1, here it will now be blocking logic. So you will actually see it as black on your screen, especially when you're using the softwares. Okay, that's why I'm trying to draw them. So please take this note, and I think it's also, I drew them also in your notes, the previous notes. So if you've checked, you would have seen that the normally open contact only changes its color to green when it's passing logic. So it's a logic 1. While the normally closed contact is actually passing logic or allowing logic when it is in the false position or it's in logic 0. That's when it is green. It's the opposite. Having said that, you can now understand why I am drawing this as is, meaning here you have logic 0, you have a logic 0 here, and you still have a logic 0 here. So that both the normally closed contact is already passing the logic, but the output is here like that. Oh, and we said we also have to, do what? We have to latch the output like that. So this is output Y. Okay, let me just, because I don't want to write the entire, let me just write Y. So let's see how this achieves the latching compared to the set and reset. Okay. Again here, remember that the scan always is from left to right, top to bottom. So the scan starts from left-hand side of the rung, moves to the right. Please note, because now here you might confuse. Here the scan is not like this. The scan does not go like this. And then it comes back and checks this one. No. The Y here, this Y here is an input now. It is not an output. So the scan always has to check the inputs. Remember, this is only one rung. This is rung 1. There are no 2 rungs here. This is just one rung. So the scans must complete all the inputs of the rung before it goes to the output. So the true cycle is such that it checks. Let me draw it dotted. It comes and checks this. The processor checks that. Okay. It will have to come and check this. Okay. That's also an input. And then it will come and check this, and then it will go to the output. This is one rung. So notice that every scan cycle exhausts the inputs of each rung before it moves to the output. Then it goes to the second rung. So if we had another rung, that's when it would come back to check the inputs of the second rung. But otherwise, because here we have only one rung, it exhausts the inputs of that rung before it proceeds to the output. So here, the scan moves and checks input A, okay? Then it checks the output Y, this input Y, not output Y, input Y. Then, oh, we did not label this. This is input B. So it checks input A, input Y, input B, then goes to the output Y. Now, if input A, let's now that we know how the scan is, let's write conditions now. If input A, I'm avoiding writing too long, and so I'll just shorten some of this. So if input A goes to true, so let's say input A is true, meaning we expect input A to turn green. And let's say input B, this is input A, this is input B. Input B, let's say, is false. Input A is true, input B is false. Okay? What happens? Now I can draw this here properly so that we see what these conditions are. So if input A is true, meaning input A will now be green. Remember, input B is false. So because it's a normally closed contact, if it is false, it's passing logic. That's when it's green. Okay? That's very important. No. This remains as so this is A, this is B, this is Y. So please note, input A is true, so that's logic 1. Input B is false, so it's passing logic because it's a normally closed contact. Input B is passing logic because it's a normally closed contact. And so the typical illustration of if A and B equals to Y. So notice if A and, let me write it properly, if was a condition, if A and B, then Y. Okay, that was the expression. So notice A is logic 1, B is logic 0. But now we know that because it is a normally closed contact, it's passing logic. So it means that if you give B a logic 0, it then provides a logic 1 to the output. If you have B as a logic 0, the output becomes a logic 1. So it's like saying if I put 0 here, because it's a NOT gate, you're going to have a 1 there. And therefore, the output will be a 1. And if you have a normally open contact, if I put a 0 here, it will just be a 0 at the output. Okay? And if I put a 1 here, which means if I activate it, I get a 1. So that is what goes to the output. Okay? So in this case also, please note, this is green. This is green because if you give this a logic 0, it provides a logic 1 at the output. If you give this a logic 1, it gives you a logic 1 at the output. So then you have 1 being transferred to the output and the output being a logic 1, because there's a path for logic to flow from the input all the way to the output. So please take note of that we have a logic that is flowing, there's a path for logic to flow from the input all the way to the output. So if input A is true and input B is false, then the output goes true. I've not included this yet because this comes usually in the second case. Because remember, this input Y is determined by the state of the output. So we have to see. So now, see what happens. We had A being active. This initially is logic 0 because we don't have anything. We still don't know the state of the output, or the original state of the output was 0. Okay. So this was 1 here, and this originally was 0. But because this was logic 0, it provided a path because it's a normally closed contact, and therefore we had the output going to logic 1. As soon as the output goes to logic 1, it then changes this to logic 1. So then the first scan cycle will come. I want to repeat that so that everybody is clear. During the first scan cycle, I've told you how it scans. It's here. During the first scan cycle, notice here that the output is at logic 0. So this is also 0. Okay? Now, let's start scanning. We go to logic A. We've said it's logic 1. Input A is logic 1. So logic B is, input B is logic 0. So we have a path of logic all the way to the output. As soon as the output gets a logic 1, then the input Y is updated also as a logic 1, because the first scan cycle will complete everything. It will check A, B, Y as the inputs, then checks the outputs. And because we don't have a second rung, then the scan cycle will complete. Then now update the outputs. So it will come and check what is in memory location A. Memory location A is logic 1. So logic is passing through. What is in memory location B? Memory location B, the state is false. So it is passing logic. Okay? So if it's passing logic, what is in input Y? It is 0. But it doesn't matter because we have a path up here. There's a path for following. We don't have to. Remember, I told you this is the OR path. So it's an alternative. But because we have a path through A and B, then this will become a logic 1. So that is just noted by the processor until it completes the scan cycle. And because this is just one rung, as soon as it completes the scan cycle, it will now update this to logic 1. Once this is updated to logic 1, automatically it's the same memory location as this input. So this is also logic 1. Don't forget that the memory address here, so if this was output Q0.1, this should be output Q0.1, but it is used also as an input. So it's like, it's the same memory location. On one side, we are using it as an output, but on another, we are also tapping it as an input. So ultimately, because we had a path that was followed here, and we got our logic 1, we had a path, and then we got our logic 1 here, we can update this also to be a logic 1. And once it is a logic 1, then it means, and this is where it's important, once this is a logic 1, it means that even if I make this go to logic 0, even if I make A go to logic 0, then there would still be a path for logic through Y, then through B, and then the output will still remain as 1. So you can see that the output is still latching, even if I make A go to 0. Why? Because I would have provided an alternative path through the input Y for logic to pass through. So let me repeat that again for anyone who might be having issues. I am saying this. Remember, we have said that this circuit or this diagram performs the same function as the set and reset latch, where you first need to convert the output state to logic 1, hold on to that state until there's a certain instruction or until another condition is met, then the output state changes back to 0 or changes back to false. And we are looking at that using this circuit, that initially, if you make this, activate this, then make this a logic 0, logic will pass through and we'll have output logic as 1. Because this output Y is the same as this input Y, if this becomes logic 1, then the input becomes a logic 1. That even if I take this back to 0, I take the input back to 0. So there would be no path through that, because remember, if there's a path, if this is 0, logic 0, there's no path. But still, because this was logic 1 already, there's now a path like that for logic to pass through. So we'll be having the output retaining the state of logic 1, even when the input A has been taken back to 0, or the logic of A is made false. We're still having the output retaining the logic 1. The only way we can now take back the logic of Y to 0 is by changing this. We make this logic 1. And we definitely know that it's a normally closed contact. So if we make it logic 1, it blocks the logic from passing through. So we have a case, I'm going to give you the notes, so don't worry. We have a case where the original, we have a case where we have the original circuit as A, then you have this circuit as B, then you have the output as Y, and then, of course, you have your output there. Here you have it as an input. So we are saying this goes to logic 1, this stays as logic 0, but because it's a normally closed contact, it's allowing logic. So Y becomes logic 1. Regardless, even when this is logic 0, even if this was logic 0 initially, we have no problem. But because there was a path here, A, logic 1, B, logic 0, that means it's allowing logic to pass through. Therefore, the output is logic 1. As soon as the output is logic 1, it updates the input here to be now logic 1, such that even if I now make this logic 0, there's an alternative path for the logic to still get to the output, so that even if it doesn't follow that path, okay, there's an alternative logic to get to the output, even if A goes back to 0. So that's the latching we are talking about. The output is still holding on to the state 1, even if I change the input A back to 0. The only way I can make the output now go to 0 is by making B equal to 1. Because if I make B, the input B equal to 1, it will then block the logic from passing through. So the output would be 0, and therefore immediately it will also change that back to 0. Okay? Because it's the same memory location. So you can actually see that we are achieving a latching here by 1, making A go to logic 1, having the normally closed contact B retain logic 0, then the output would be logic 1. Such that even if you reduce or you return back the logic A to 0, the output will still be held at logic 1. The only way you can reset that output is by changing B to be logic 1. Okay? So again, I'm going to give you notes that illustrate that step by step. Okay. I hope that is clear. Now, if we are to strictly look at this now, if somebody told you, can you come up with a logic expression for this circuit? Let me put it back the way it was. Let's come up with a logic expression for this circuit. Let me put it back like. So we had to latch the output as an input here. So this is A, this is B, and we've latched, and this is the output. I told you the logic expression is very easy to find. So you have if here, between A and B, of course, is AND. between A and Y, of course, we know is OR, because parallel, connected in parallel, or if it's branched out, that's an OR. It's a branch, meaning it's an alternative. That's why we are saying it's an OR, a branch, an alternative. So if A and B, of course, here we usually say between the input and the output is the word then. So if I were to write this out properly, I would write if is part of the instruction. But now notice it is A or Y, A or Y, because that's the first part. You have to do A and Y. I mean, you have to check this and this. Remember how, and then you go back to, remember how I drew the, I don't know whether it can be seen in green. I said you come like this. That's an input. You have to check this input as well. Then you come and check the output B. I mean the input B. Then you go to the output like that for branching cases. So that's why I'm saying if A or Y, because the relationship between A and Y is OR, and then AND comes after that. And then, of course, B, but now in this case, you don't say B, you say not B, then, because it's a normally closed contact, that's why I'm saying not, it's like a not gate. Then, of course, you have Y. So that's the logic expression. If A or Y and not B, then Y, or the output Y. So, ladies and gentlemen, I want you to understand that the latching logic is a very, very important logic because it helps us to simplify the code. If you compare this code, if you compare these two codes, the first one, remember, was using the set and reset. I'm drawing them again just to make sure the point syncs. So set, reset, A and B. So we use this circuit to achieve a set and reset. The next circuit that we have now used is this, where we have just used one rung. This circuit. So this is now A, of course B, sorry, what am I writing? This is Y. This is B, and of course this is the output Y. So we have said that these two circuits are equivalent, meaning the outcome given by the circuit number 1 is the same outcome given by circuit number 2. And we've illustrated that. However, between 1 and 2, it is circuit number 2 or diagram number 2 that is simpler. The simplification of a ladder diagram is based on how many rungs you have used to achieve the same outcome. The first ladder diagram uses 2 rungs to achieve a latch. Okay? So to achieve a latch, it uses 2 rungs. The second ladder diagram that we have used is only using 1 rung. So here we've just used 1 rung to achieve a latch. Okay? So between these, this is the simpler ladder diagram because we are only using 1 rung. So it means the processor time would be shorter. The scan cycle for the second one would be faster. The scan time would be shorter than the first ladder diagram. The time it takes to scan through the second ladder diagram would be shorter than the time it takes to scan through the first ladder diagram. So this is a simpler ladder diagram, the hold-in logic, and so it is more preferable. Number 2, If you were to do troubleshooting or you are debugging your ladder diagram, it would be more difficult to debug the first ladder diagram because, like I told you, the first ladder diagram, the set and reset don't have to follow each other in their ranks. You can find that this is rank 4, maybe, and this is rank 17. Okay, meaning there are other ranks in between them. So checking where the problem is could take longer, or it could be more difficult or complex. But for the second one, the holding logic, you can see you're only dealing with one rank, and you have the inputs and the outputs on the same rank. They're not on different ranks. So you're able to follow it easily. Okay. So all the conditions that releases the latch is in the same rank. Here, you have a condition that sets the output. The condition that releases the latch is in another rank. Okay. But here, the condition that releases your latch is in the same rank as the condition that sets the latch. So you set the latch and reset it from the same rank. But in the first case, you set and reset from different ranks. Okay. So this guy is simpler and easier to troubleshoot. And so it is the one that is most preferable, especially for your case as students who are still learning. It's important that we use the holding logic to help us when we are setting up ranks. Now, the best way to do this is now to use examples. So allow me to spend the next few minutes to do the first part of the example. We'll complete it on Wednesday. I just want to go back to the mortar case, okay? So let's do an example. I'm sure we won't complete. We'll do the first part of the example and then we'll complete it in the next class. So now I wish I could. Okay, I'm going to share these notes with the class rep immediately after this. So
Excuse
that
me, sir.
Yes, go ahead.
Yeah, today we had a really rainy morning and you have a class at from 10 a.m. physical. I don't know if the others will agree, but could you maybe spare us a few minutes and maybe on the Wednesday class you could get 30 minutes extra after the 1 hour class? I don't know if the rest will agree.
Oh, so you would wish that I release you now so that maybe you catch up with your physical class?
Yes.
But on Wednesday we will have a makeup class from 9. So even if you release us, we cannot extend on the day as some are suggesting.
Okay, fine. Let's do this. I'm going to send you guys the notes today. You can follow them up later in your studies. And then Wednesday, we have a 1 hour class. So we'll just do that 1 hour. There's no problem. Unfortunately, we have to look for a makeup class. The reason is I have been asked to go and attend a 1 week long seminar where we are trying to introduce biomedical engineering. So we have to come up with a course outline. And so it means the whole of next week, I will not be available. We'll be retreating somewhere. So it means that either way, we have to organize ourselves a makeup class. So let's do this because I also have to let you go catch up with the class. Let's leave this here. We'll continue with the example. I'm going to send you the notes so that it's easier to follow. Then when we meet on Wednesday, we can quickly run through the example together, having gone through it. But we'll need to look for a makeup class later. We'll agree on the best time, whether it's physical or online, we'll decide. But the whole of next week, I will not be available. So we'll organize with the class rep and in conjunction with the class to see when we can have a makeup class at least, because we would have wasted a whole week, which is 3 hours, and we need to catch up. So is that okay that I give you the notes? You go and study on your own. Wednesday, we'll just do 1 hour, which is fine. And then we'll look for a makeup some other time later. Sawa sawa?
Yes, thank you.
All right. Okay, ladies and gentlemen, thank you very much for listening. Please take the notes from the CR as soon as possible. Let's end the class here so that you can catch up with your next class. Remember, I would also want to resume physical classes from after I come up from the retreat. So I hope we'll be able to catch up together. So thank you very much and have a good day. Goodbye.